Hi, welcome everyone to lecture number 8 of the subject control system. Uh, Till previous lecture we discussed about various modeling technique of physical systems like translational mechanical system and rotational mechanical system. Then we learned the analogies, that is force voltage analogies, force current analogy, torque voltage analogy and torque current analogy. After completing those portions, I am going to another kind of representation of another kind of modeling technique, that is block diagram representation. In block diagram representation, what we generally do is we assign blocks to each and every system or each and every single element of the system. Okay, so this kind of representation will be there in block diagram representation. In each block, the transfer function of each system will be there, and this will be the input x, and this will be the output y of s. Okay, this kind of representation is block diagram representation. Now if I have various kind of subsystems, one is having transfer function g1, g2, g3, etc., and that can be that are physically actually connected in such a way, we need to represent that in terms of some blocks. Let's say we have systems like G1, G2 and G3. We have three different subsystems, and our total system is like this: G1, let's say it is connected in cascade with G2 and some feedback will be there, G3. The system is, let's say, like this. Okay, so now how we can evaluate that, how we can analyze the total system, because the total system, this kind of block diagram can be again represented by a single input output system with a single block representation. The total response ys will be the response of this system, that the main input rs will be, that is a reference input if it is a control system, then that will be the input to the overall system, and this overall system can be further represented by another block. And how and again, to analyze each portion of the system, each subsystem, we can use these transfer functions like g1 is a transfer function, g2 is a transfer function representing another system, g3 is a transfer function representing this system. Okay, so to analyze individual systems, we can analyze this transfer function g1 or g2 or g3. But let's say I have a system, yes, I am worried about the individual response of those systems. I need to analyze the individual system, but as a whole, how the system works is so much important for us. So I need to analyze that system as a whole with this kind of interconnection. Let's say my system has this kind of interconnection, and I need to analyze this system as a whole. But look, whenever I have G1, G2, G3 components separately, it is not convenient for us to represent the whole system, to analyze the whole system as a whole. Okay, so we actually represent the combination of blocks into some, we actually reduce to a single block, and that will be through transfer function, that will be through block diagram reduction techniques. And after reducing the block, there will be a single transfer function that will be, let us call it a GS, where G is the combination of G1, G2 and G3. Based on the combination, based on the interconnection, value of G will be different, but it will represent this total system along with the interconnections. So how we can arrive to single block of any system representation, that will be see that will be see gradually. Okay, now what is happening, we know. Okay, what we know is transfer function of any system, is Laplace transform of its output by Laplace transform of its input. It is called G of S, provided initial condition 0, initially relaxed. We know these things. Okay, so if this system is initially relaxed, then what will be the Laplace transform of output? Laplace transform of output is Y of S. What will be the Laplace transform of input? The Laplace transform of input is represented by X of S, because X is the input, Y is the output. So Ys is the Laplace transform of output, Xs is the Laplace transform of input. And as we are dealing with transfer function domain, so we are considering this system was initially relaxed. This system is initially relaxed. So how we can write G of S? G of S, we can write it as Y of S by X of S. Now again, I have a system, I have the transfer function, I know what kind of input I am giving to the system. Then obviously from this equation I can easily calculate the output expression like this. By simple mathematical manipulation, Y of S will be G of S into X of S. That means transfer function into the input, all in Laplace domain, will be equals to the output. Okay, so this is actually the use of block diagram and transfer function. Now I am gradually going towards the reduction techniques. Let's say now, having said this, Ys equals to Gs into Xs, I will use this relationship in my next elaboration. Let's say I have a block diagram like this. Let's say I have two subsystems, G1 of S and G2 of S. Let's say I have these two subsystems. Here I am not concerned about what this G2 is, why this G2 is used, or why this what kind of work this G2 is performing, or what kind of work this G1 is performing. I am not worried about that. But what I am worried about that is I need to analyze this system as a whole. But I can analyze G1s, but that analysis will be for this block only. I can analyze the transfer function of G2s, but that will be the analysis of this portion only. But together as a whole, with this interconnection, how the system works, I don't know. To analyze that thing, I need another transfer function which will be equivalent transfer function. Let's call it as G of S. Let's call it as G of S. This transfer function will represent the total system, the total portion of the system. And if I analyze this transfer function, then I can analyze the total, the two of the system. The total system comprises these two individual subsystems. Okay, let's say this system have some input Xs and some output Ys. So obviously if this portion is represented by this block Gs, then Xs will be here and Ys will be here. Now how we can arrive Gs? This Gs will be some function of G1 and G2, right? So how we can arrive to this equation, to this transfer function? Let me analyze like this. Okay, let us say you have G1 only, you are giving some X1 input and you are getting some Y1 output. If you give X1 to as input to G1x, G1s, then you will get Y1s as output. So what will be the expression of output? Y1s, as I just said earlier, Y1s will be equals to G1 of S into X1 of S. Now if I have another system like G2 of S, here I am giving the system X2 as input and getting Y2 as output. So what will be the relationship between Y2 and X2? Y2 of S will be G2 of S into X2 of S. Now look at this system. This system, this is the individual analysis. This is the individual analysis. Now I am going to do the analysis throughout the system, through the whole system. Okay. x1s, if I am giving x1s, the output y1s will be g1x into x1s. So what will be the output here? If I am getting xs as input to g1s, it will be, let's say, zs, and zs, what will be the value of zs? Zs will be xs into g1 of s. Now instead of giving x2s as input to g2s, I am giving zs to the input of g2s. Now what will be the output of g2s? That is ys here will be equals to zs into g2s, z of s into g2s. So this zs will be xs into g1s, and this g2s will be zs into g2s. This y2s ys will be zs into g2s. Okay. Now put the value of zs in this equation. What we will get is y of s will be equals to zs into g2s, and in place of zs I am putting xs into g1s, because zs equals to xs into g1s, xs into g1 of s into g2 of s will be there. So what will be the value ys by x of s? That will be equals to g1 of s into g2 of s. So if I represent this system, this overall system, as a single block like this, g of s, where I am getting output ys with input x of s, I am getting y of s output using this x of s as input. So what I am getting is g of s equals to y of s and by x of s. That means g1 of s into g2 of s. So whenever whenever two or more blocks are in cascade with each other, then the overall transfer function of that total system will be multiplication of the transfer function of each blocks. If it is z1s, g1s and g2s, then the total system will be g1s into g2s will be equals to g of s. If there is another block g3 of s, and let's say this is z1s, then z1s equals to x of s g1s. g2s will be taking input as z1s. Let's say it is generating z2s as output. Now z2s will be equals to g2s into z1s, where z1 is equals to g1 into x. So z2s will be equals to g2s into g1s into xs. Similarly, ys will be equals to g3s into z2s. Now z2s is itself g2 g1 x, so ys will be g3s g2s g1s xs. So the system will look like ys is the output, xs is the input, and the transfer function between between these two variables, a single transfer function, will be g3 g2 g1, the multiplication of these three. So if two or more blocks are in cascade, then the transfer function of the overall system will be just multiplication of the individual transfer functions. This is the first technique, first reduction technique. Now the next thing will be a closed loop. Let us call gs as a forward transfer function. Okay, from input, if signal line is from input towards output, the arrow is from input towards output, then those lines, those path will be called as forward path. And if the input line is feeding back from output towards input, then that will be called as feedback path. Okay, let us say we have a feedback element h of s, it is another system, let us say it is a measurement unit. This GS is the combination of system of a plant and a controller. Okay. So now I said that there will be some comparator. Okay, how the system will work? The system actually, okay, let's consider this GS as a controller block cascaded with a plant block, and as a whole I am using the rule for cascaded systems to reduce it to a single block GS. Okay, so now what happens is this block is called a summing block. This block is called a summing block. If two signals are coming towards this, okay, and one signal is going out from this summing block, then based on the sign, let's say you have two plus signs here, and here you have x1 of s, here you have x2 of s, then and you as output of this block, this is called a summing block. If you have output ys to this block, then ys will be equals to the summation, that means based on the sign, if there is negative sign then that will be different, like ys will be the summation x2 and x1, x1s plus x2s. This is called a summing block. Now if let's say this block is negative, this portion, this port here is negative, this input portion, then it will be x1s minus x2s. If instead of being negative in this side, the negative sign is in this side, then it will be obviously x2s, x2 of s minus x1 of s. I hope it is clear clear to you, the summing block, the working of a summing block. So now why I am subtracting this portion of the this portion of signal from my RS. Let's say, let's consider this is a control system. Now this control system needs to accomplish some goal, and the goal is to minimize the deviation of the output. Let's say output is CS. Often in control system, C is denoted by, sorry, output is denoted by the letter CS. Okay, and RS, it is the reference input. So what will be happening is this HS will feed a portion of this output towards the input side, and RS, this summing block, or this can be also called a comparator, because this will compare this RS and the feedback signal here. If it is a feedback signal, let's say, let us call it as B of S, it will generate, generally what it will do, this summing block or comparator, it will compare RS and BS by subtracting BS from RS, and it will generate some error signal E of S, and that error signal will be fed to the controller, and controller will command the plant to control the output. This is the case here. Now if you have this kind of block diagram, and you need to analyze the total system as a whole, let's say this is the total system, and you need to analyze that one, how you are going to reduce it to a single block diagram. How you are going to reduce this single block diagram? Look, okay, I discussed about summing point. This is blocks, these are called signal lines, and this portion is called tapping point. How this tapping point works? If you have a signal line which carries signal as x of s, and you have a tapping point, let's say it is going in forward direction or in reverse direction, that is not our concern. But if you take a tapping point from this signal line towards any direction, then at the end of this line, or this line will also contain the same information, x of s. If you have a signal line of xs and you have some tapping point on that line, then the tapped line will also contain the same information xs. So if it is this line is carrying cs, then through this tapping point this line will also carry c of s as the signal towards hs. Okay. Now what will be the expression for bs now? As obvious, if now here hs is taking input as cs and giving output as bs. So what will be the value of bs? Bs will be h of s into cs, isn't it? Bs will be h of s into cs. Now I want to obtain a single transfer function for the whole system. That will be, let me call that as T of s. Okay, T of s. Let me call it as T of s. So the input to the whole system will be Rs itself. The output to the whole system will be Cs itself. So what will be the value of Ts? Ts will be Cs by Rs. So if I can find a relationship between Rs and Cs from this diagram, then I can find that single transfer function from this for this block. Okay. Now we have E of s, we have C of s equals to, as you can see, G of s is taking E of s as input and giving C of s as output. So what will be the value of C of s? Gs into E of s, G of s into E of s. Now this will be the output. Now what will be the value of E of s? We know the G of s because we don't want to disturb this G of s and H of s because these two things are in my hand, but I cannot directly measure these things in order to obtain the transfer function. Okay, this is the scenario. Now G of s into E of s. Now E of s is equals to, again, E of s can be written as Rs minus B of s, because from this summing block there are two inputs, or for this comparator there are two inputs, one is Rs, another one is Bs, and the output of the comparator is Es. So Es can be written as Rs minus Bs. Having said that, I can put the value of Bs, again the value of Bs as I have derived earlier, the Bs will be equals to H of s into C of s. So I can write E of s as R of s minus B, in place of Bs of s I am going to write H of s Cs. Now this Es will be put here, sorry. Okay. So what will be the value? C of s will be equals to G of s into E of s. That means G of s into, what is E of s? E of s is R of s minus H of s into C of s. Now just mathematical manipulation, G of s into R of s minus G of s into H of s into C of s equals to C of s. Now this term here is having C, this term is not having C, and this term is having C. So taking C in same side, this will come here, and C of s I am taking common, and it will be 1 plus G of s into H of s, and this will be G of s into R of s, G of s into R of s. Now C of s by R of s will be equals to G of s by 1 plus G of s into H of s. So the total transfer function, that is C of s by R of s, will be equals to G of S by 1 plus GS HS. GS by 1 plus GS HS. So if you have this closed loop configuration with negative feedback, why it is negative feedback? Because in the summing block is actually acting as comparator here, because one input to the summing block is in negative sign. That is why the feedback line is subtracting from the input. The feedback line, the feedback signal is subtracting from the input, is being subtracted from the input. That's why this is called a negative feedback system. The feedback line is negated and then fed to the comparator block. Okay, so when there is a negative feedback system, the transfer function will look like this, the overall transfer function. Now in control system, often you will consider, come across this kind of thing. One is OLTF, that means open loop transfer function, and another one is CLTF, that is closed loop transfer function. What is open loop transfer function? Obviously for open loop configuration, let's say G1S and G2S. So what will be the open loop transfer function for this? It will be G of S equals to G1S into G2S. Now if you have said that there is a feedback HS and the open loop transfer function is G of S, then what will be the control system? The control system will look like the open loop transfer function G of S, that means the open loop configuration, the transfer function will be like this, and the feedback path we having one H of S block, that means H of S. So this will be feedback, and obviously this will be negative feedback. For controller we often consider the negative feedback. Okay, why we consider negative feedback? I will give idea for that also. Okay, so this is the same will be there. Now if the overall transfer function, that means GS by 1 plus GS HS is given, then that transfer function will be called as CLTF, because the transfer function will be closed loop transfer function of the control system. Now if the transfer function is only GS mentioned here, that transfer function will be open loop transfer function. Okay, and obviously whenever open loop transfer function is mentioned, either it is happening like you need to consider, analyze only the open loop configuration case, or if you need to consider the closed loop transfer function and you need to obtain the closed loop transfer function from this open loop transfer function, then obviously what will be the feedback transfer function that will be given. If not given, there will be something mentioned like unity feedback. If unity feedback is there, then the gain of this block will be considered as unity, that means 1. If it is unity feedback, then what will happen? Then if HS is 1, now BS equals to HS into CS. If HS is 1, then obviously BS will be equals to CS itself. So there is no need to draw this block. For a unity feedback system, the system will look like this. This will be closed loop diagram, and the transfer function here. Now again, don't consider that GS, there is no transfer function in the feedback loop, so only GS will be the closed loop transfer function. No, GS will be open loop transfer function only. For closed loop transfer function of this kind of system, you need to put HS equals to 1 in this expression. If you put HS equals to 1 in this expression, what will you get? You get GS by 1 plus GS. For unity feedback system, for unity feedback closed loop system, the open loop the closed loop, if open loop transfer function is GS, the closed loop transfer function will be GS by 1 plus GS. I hope this is clear for you. Now I am putting aside the block diagram reduction technique, rather right now I want to do something else. That is, we in the first lecture we discussed the control architecture as there was a controller. The controller was commanding the plant to make the output as desired level, and the output was fed back by some measurement unit sensors, by some measurement unit. This was informed to the controller, and controller controls the plant by taking some reference input. This was some reference input, and this was the measured output. This was desired output, that means reference input is equals to desired output. This was measured output. Thus the plant was controlled. Now we know the block diagram. This is a simple block diagram, but this is not a detailed block diagram of this kind of system. What is happening, I am trying to draw one block diagram, one pretty detailed block diagram. That is, first you have some plant, there will be a summing block, okay. So this is a pretty detailed block diagram of the closed loop control system. In the first lecture I discussed about closed loop control system, but we haven't learned then the block diagram technique, what is summing block, what is different kind of blocks, and how we can how we can obtain the open loop transfer function, how we can convert the open loop transfer function into closed loop transfer function. We didn't know that. That's why I didn't discuss this portion earlier, but this is the high time to discuss this one. So this is a total closed loop control system. This is the main automatic control system. Okay, it in a general idea. Now this is the plant. This plant is to be controlled. Okay, now the plant have some output. Let us call it some output is CT. Now why I am denoting the output here instead of this? Because this is the actual output of our system. Our system is the total portion of the system. So plant output plus some dt will be equals to our main output, that will I get from the system. Okay, so what is this dt? As I said earlier, dt, or you can also call it wt, as disturbance, and this disturbance can be from outside the system, and this in this diagram it is drawn in such a way that it seems like the disturbance is from outside the system, but this can be inside the plant, but this is represented by some outside signal. Okay, this is disturbance. The plant output plus the disturbance will be the main output of our system, and the effect of this disturbance need to minimize. Let us say the disturbance, it is a very intuitive idea, it is not the actual case. Let us say plant have given output as 5 and there is a disturbance 2 and I am getting, let us say, 7. If it is 5 and if it is 2, then obviously the output will be 5 plus 2, 7. Now my objective is to get the output as 5, not 7. My objective is to get 5. Here I am giving it as 5. So what it will do, the controller will actually actuates the plant, then it will reduce the system to a value 3. And now, though the plant is not now giving me the correct output, which I am desiring, but from the output port of the total system I am getting the 3 plus 2 as 5 and my desired value was 5. So I cannot control the disturbance, but I can control the effect of the disturbance which is deviating my desired value. Okay, so this is not the case actually, but for understanding purpose this is happening inside the control system. Okay, so what are different signals here? I need to name the different signals. This is obviously the response of the system, the total system. This plant is to be controlled. Now this response is measured by the measurement unit. So this portion will be measured output. Now again, why this LPF is used? Remember, while discussing about the disadvantage of this kind of closed loop control system, I mentioned that any sensor or measurement unit actually has some high frequency noises. So this actually will be, and that high frequency noise is injected in that loop. So this signal is actually not only the measured output, it is measured output plus some high frequency noise, plus some noise. Now if I use some low pass filter, then it will cut the noise out and it will provide the measured output only at the output side of the LPF. So here you will get pure measured output. Okay. Now this is input sensor, and also this input sensor also give you some high frequency noise. You can use another low pass filter here between this sensor and comparator. However, I am not drawing it here. You can use that. Okay. Now, sorry, this is and this is a negative feedback system. Okay, this is measured output. Now you are giving some reference input. If you are giving some desired output, let's say it is you who are giving the desired output, or let's say another system which generates some output. That output will be some desired at the output of this system. Okay, so this will be desired output, and that desired output will be converted into some electrical equivalent using input transducer or input sensor. And also this response is also measured and measurement of some physical parameter means some electrical equivalent will be there, and after that LPF, the pure measured value of that equivalent electrical quantity will be compared with the electrical equivalent quantity of desired output. So electrical equivalent quantity of desired output minus electrical equivalent quantity of measured output will be fed to the controller, and this will be the error signal. As you can understand, obviously this will be the error signal. Controller will take that error signal and it will generate some control output. This is called control output. The controller will generate some voltage or some current or some other signal, that is called actually control output. Now what is this actuator? Actuator actually actuates the plant. Let's say control, as I said earlier, the level control system, where you were actuating a stem position of a valve. Okay, the stem position of a valve was actuated by giving some signal to the stem position of the valve. So the actuator, actually controller will generate some voltage, but that voltage cannot force this valve to move forward or backward. That's why we need another device that will understand the meaning of the voltage, and that voltage will actually drive the actuator, and the actuator will actually convert that voltage signal into some pressure signal, and it will force the stem of the valve to go down or to come up, and then it will, doing so, it will actually manipulate the outlet flow of the system I discussed in the first lecture. So there will be some manipulated variable. This variable here is called a manipulated variable, and manipulated variable, by manipulation of manipulated variable, plant will change its response and you will be getting the desired value. So this is the total architecture of closed loop control system. This is the total architecture of closed loop control system. Now I just said that closed loop control system, the only negative feedback is used in case of closed loop control system, but the positive feedback is not used for closed loop control system. Why is that so? What is negative feedback? The negative feedback is denoting this negative sign here, this negative sign denoting the negative feedback. So what is the main objective of the controller? The controller will take input as error signal and give some output as control output. Now if the response is not desired value after the controlling done, then also there will be some error signal, and based on that error signal, controller will change the control output. So controller will continuously try to minimize this error signal. If this error signal is ideally 0, then desired output will be equals to the measured output, that means response. In response you will get the desired output. So controller will continuously try to minimize this error signal. Now if instead of doing a negative feedback here, if we do a positive feedback, then the desired output and the measured output will be added together, and if it is added together, then error signal cannot be minimized, because error signal based on there will be some error signal, based on that controller will increase, let's say, and response will again increase, and the error signal will be increased further, because desired output will be same, response will be increased, and error signal is the summation between the desired output and the measured response, actual response. So error signal cannot be minimized. Talking mathematically, let's say, okay, let me do some mathematical interpretation. The simple closed loop negative feedback transfer function block diagram, that is this one, H of S E of S. So what was E of S? E of S was R of S plus minus B of S, isn't it? And B of S was representing the output C of S. Let us consider the system is having positive feedback. So instead of being R of S minus B of S, the error signal will be R of S plus B of S. Now controller will try to minimize the error signal, and what will happen? It will minimize the error signal to 0, then controller will understand that okay, the system is giving now the desired value. But what actually happens inside is RS will be negative of BS. That means the output which I want to get, I am not getting the output, rather what I am getting, the completely opposite of my desired value. Then only the error signal can be 0. But that is not my objective. I need the same output as I am getting. That means that I need the output as the same as the desired output. But if it is positive feedback, instead of being the same output, it will be totally opposite to the desired value. That means, let's say I want 5, I am getting 2 here. Then what will it do is, if it is a negative feedback system, ideally what it do, how it does actually, I want to get 5, this is a negative feedback system, let's say this is unity feedback. In order to simplify the things, I am considering this to be negative unity feedback. Okay, the output response is 2, the desired output is 5, so the error signal will be 3, so GS will increase its output. Now it is, let's say 3, so the error signal will be 2. Look, the output, the measured output is approaching towards the desired output and the error signal is minimized, error signal is reducing. Now it is 3, it is 2, again this will again increase the value, let's say from 3 it is now 4, the error signal is now 5 minus 4, that is 1, and it will again increase, the error signal will be 0, and the controller will know that okay, my job is done now. Now if instead of being a negative feedback, if it is positive feedback, then what will happen? Let's say the same scenario, my output is 2 here, so what will be the error signal? 5 plus 2, 7. Controller will understand okay, there is so much error, so I need to increase 3. Controller will now know 5 plus 3, that is 8. Okay, I am increasing this output of the system, but my error signal is also increasing. Now if my error is increasing, controller will try hard to actually make the output go higher, so it will generate 5, let's say. Now actually this 5 is same as this 5, so the controller ideally should stop, but what controller will know? Controller will know the error signal is now 10, so it will further increase and it will be 10, let's say, then it will be 15, then error signal further increases, so it will be going to the verge of instability. The system will blow up, the system will not stop at any point. Now what can be done is, the controller can reduce the system, reduce the output. Let's say I have 7, okay, the thing is 5 plus 7 is 12, the controller know that the output must be reduced, so it reduced to 6, then 5 plus 6, it will be 11. Now look, the output is approaching towards the desired value and the error is minimizing. Now it is giving 5 and it will be then 10. Now still there is some error, so it will try to make it further less, let's say 2, then it will be 7. Now again look, now the output is going away from the desired value and the error is minimized, error is reducing. Now it is at minus 5, let's say, then the error is 0. So I want 5, I am getting -5 and my controller will say to me at this time that the system is at steady state, the system is controlled, because the error signal is no longer there, error signal becomes 0. But that is not my objective, I don't want -5 here, I want +5. So positive feedback will actually, what it will do, positive feedback actually take the system, positive feedback actually pulls the system towards the instability, the system output gets blown up. So this is block diagram reduction technique. I have just discussed two kinds of block diagram reduction technique. One is the cascaded block. If two or more blocks are cascaded, then the single block will be represented by the multiplication of the individual two or more blocks. And if there is a negative feedback system, then negative feedback system with open loop transfer function as GS and feedback system as feedback transfer function as HS, then the system overall transfer function will be TS will be GS by 1 plus GSHS. And then we discussed about the total architecture of closed loop control system using a detailed block diagram. Then we discussed why we cannot use positive feedback for control applications, because it will the control system will be unstable. Now there are a lot more techniques of block diagram reduction that will be discussed in the next chapter. I think the time is over, so in not in the next chapter, but in the next video lecture, that those things will be discussed. This much for today's lecture. Thank you. Goodbye.